Question of the Week from the Naked Scientists.
Hello and welcome to Question of the Week with me, Izzy Clark. This week we're focusing on a question from David.
While walking my dog in the evenings during the holiday season this year, I noticed I was unable to focus on and clearly resolve the dark blue LEDs in Christmas tree lights or fairy lights. For all the other colors, I could resolve the shape and even the texture of the individual light bulbs, but with these deep royal blue LEDs, all I could see was a hazy blur. Why is that?
Here's Dr. George Dobray from the University of Kent to shine some light on this colourful query.
The cells in our eyes that process color are called cones. It's easy to remember, cones for color. And they can be found at the back of our eye, called the retina. These cones really detect just three colors, red, green, and blue. We then build other colors based roughly on the amount of red, green, and blue the cones report to the brain. However, the blue cones are a small minority, only about 10% of the total.
So each cone is set to tell the brain about mainly one of these three colours. But as more cones register red and green light, blue is at a slight disadvantage. But why does blue light appear blurry?
To be able to see a tiny dot of color, like a blue LED, in detail, the eye needs to be able to focus that LED light on just a small number of cones. The smaller this area can be, the more detail we can see, but for a blue dot that's difficult to achieve. The eye automatically adapts to see red and green with the sharpest focus, which leaves the blue unfocused and fuzzy. This is called chromatic aberration.
The human eye has evolved towards a compromise. We still see sharp images most of the time, except for when we look at tiny blue dots or lines. And that's because it's a relatively rare occurrence in nature. That's the anatomy and physiology part covered. Come on, George, hit me with some physics.
The physics part of the answer has a lot in common with the question, why is the sky blue? Which also applies to these blue fairy lights. Being at the short wavelength end of the visible spectrum, when blue light hits air molecules, it scatters much more than red or green. In contrast, red light at the long wavelength end of the spectrum tends to scatter less, continuing along in mostly a straight line, which is why we get red sunsets. The consequence is that blue light is focused to a spot on the retina that's a little bit bigger than that for red and green.
There we have it. It's a combination of our eyes adapting better to red and green light, plus the fact that blue light scatters across a larger area on our retina. Next time, we'll be tuning into John's musical matter.
As all sound is simply vibrations in the air, and therefore musical notes are the same, then why do we hear the same note as a different sound when played on different instruments? Why does an A sharp played on a piano sound different from an A sharp played on a trumpet?
If you can sound out an answer, email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or join in the debate on the forum. That's nakedscientist.com/forum. Until next time, goodbye.